Hello, wonderful Algebra 2 students. This is going to be our last TGA. So those of you who are with me in class, those recordings are available. So you can go ahead and click on these links and that class recording. But I wanted to make just a pointed one to support those students who are working asynchronously and might have some questions about the TGA. All right. So I have it downloaded. You'll see that it's due today. This is one of the versions that we worked on in class, but I'm going to start right here. So let me move this. Whoop. Always start with reading the question. I don't always start with reading the question, but it's a bad habit. It's a terrible habit. I'm a bad math student, and I don't do as I do. Practice those wonderful, healthy habits for that great critical thinking. Okay, nothing's wrong with my wrists. I just get carpal tunnel-ish type things where they get weak. Anyway, and so I wear this throughout the day to give my wrists a break and type. There are 25 students who started computer programming in elementary school. Well, they'll be wearing these. No, I'm just kidding. They started computer programming in elementary school. 25 students who started computer programming in middle school. The first group, so those who started in elementary school, had a mean final project with a grade of 95%. That's the mean of that group of 25 students. So not everybody got 95. Some probably got 100. Some probably got like 80. But when you add them all up and divide by 25, the average score on the final project was 95%. The second group, the students who started computer programming in middle school, had a mean final project grade of 92%. Again, those 25 students, they didn't all score 92%. Well, they could have. The odds of that are very low. But each of their grades, you add them all up, divide by 25, and that was their average grade on the final project, the mean score of 92%. Okay. The line plot shows the differences after 10 re-randomizations. Determine whether the difference in the means of the two groups is significant based on the line plot. Explain your answer. Okay, so first, the very concept of a difference of means, we have what's called our sample mean. So we have, well, it could be your population. So no matter what, they don't really tell us. But we know we have 25 students who started computer programming in elementary school. We'll call that group 1. We have 25 students who started computer programming in middle school. We'll call that group 2. And we know the mean score for that group. 95% for group 1, 92% for group 2. The difference in means is exactly how it sounds. 95% minus 2, 92% is 3%. So there's a difference. We can see there's a difference of 3%. The students who started computer programming in elementary school scored higher on average, the mean, on average by 3%. That's kind of what we're looking at here. It was like, wow, their average score is 3% higher. Is that statistically significant? Now, we ask ourselves this question, the people who might want to know the answer to this are maybe curriculum writers and educators and public school leaders who want to know, should we start introducing computer programming to our elementary students? Should we include that option, that course? When I was in school, we had typing, and I started in elementary school. I started learning how to type correctly, not with your little thumbs, or this little thumb, I don't know. I've seen lots of wild ways of typing nowadays, which is fine. But I learned how to type correctly, and I started that in elementary school. Well, if this is statistically significant, we can figure that out by re-randomization, and I'll talk about that in a second. The first part is just finding the difference. So let me scroll down. Group 1, Group 2, the difference of means. Okay, so we got that. We can use re-randomization to see if it's a good idea, if it's statistically significant to start those students computer programming in elementary school. What we want to do is, the way re-randomization works, and this is kind of the concept to try to get around our minds. I too had to learn with you guys. I haven't heard it taught this way. This concept, I haven't heard it taught this way. So I was a student with you guys as a student. So let's see if we can wrap this up. Re-randomization, the process is they list all of the 25 scores from group 1 and the 25 scores from group 2. They put them all in one group. Now they're in one big group. They use a table of random digits. They do a random generator. Somehow or another, they split them back into two groups, right? But now the groups that we're looking at in this re-randomization will have some from who started in elementary and some who started in middle school. They're going to do that 10 times. They're going to separate the groups. They're mixed groups. They're re-randomized groups. They did that 10 times and got the difference of means between the groups. And here they plotted it. So notice after our re-randomization trials, meaning this is the difference of means, when we look at the average score where groups of students are, some started in middle school, some started in elementary school. We'll look at the most common difference in means. It's still 3%. When you see it plotted here, it actually shows that it's not significant. It's not significant because we showed that no matter if you had a group of students who started in elementary or middle school and you compared their scores to each other, their average scores, you were still likely to get a 3% difference. So that 3% difference in means could just happen by chance. It could just be those students. So it's not showing that the people who started in elementary school had a much better advantage. It didn't. So we say it's not statistically significant, so we don't need to start computer programming in elementary school just yet anyway. That's just one of the ideas behind this question. The strict way of how to solve, you take the two means, you subtract them. You found the difference is 3%. That's perfect. That's the standard you'll do for all types of difference of means. You just subtract them and you find it. The next part, using this method, you do the re-randomization, and if they give you the information, you look to see if your difference of means from the original groups, the unrandomized groups, which is 3%, is plotted on there, and how frequently. If it was not very frequent and most of your data was away from your difference of means, we could then say it is statistically significant, because through re-randomization, we showed that's not just going to happen by chance. It's not common. It mattered which group you were in. That difference made a difference. That's kind of the thing. So that's the idea of statistically significant. Even though 3% is small, if when we re-randomized them, it wasn't a common difference, like that there was no X's here or only one X and most were down here or up here, then we could say, ooh, that's a statistically significant difference. So I hope that kind of makes sense. We're going to move on. Question 2. All right, let's just look at it. There's the answers, but here's the idea. Okay? The frequency table shows information that a pet food company wants to know. So they took a simple random sample from a targeted population. What is the estimated mean for the population? Explain your answer and show your work. Okay, so there's the mathematical explanation. Means are always going to be total divided by total, right? I mean, total sum divided by total. So if they want to know the number of pets owned by adults ages 21 to 70, we could think of setting this up as a mean, a ratio, pets per adults. But in order to do that, we need to get their totals. So we need the total adults, which if you look at that bottom row, you see the bottom row right over there? Right there, right? That bottom row. Add all those up and you'll get the total number of adults in this sample. That's going to be your denominator down here. See that? Plug that in your calculator. Then to figure out how many pets, we need the total number of pets if we're going to get number of pets per adult. Estimated mean. Yeah, average pet. I guess so. Proportion. Anyway, don't worry about that. Okay, this row up here, the top row, this one. Well, we can't just add 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 because each adult below, in the box below, has that many pets. So there's 248 people who have just one pet. That's 248 pets. There's 567 people who have 2 pets. That's 2 times 567 for the total number of pets. Does that make sense? And so you go down the line. You would do 248 plus 2 times 567 plus 3 times 1,402 plus 4 times 728 plus 5 times 419 plus 6 times 456 plus 7 times 203. So you should get 14,752 pets. We've often called that a weighted mean, but really it's still just the regular way of finding the average, because remember, multiplication is repeated addition. So we're just adding up all of those pets. So if we have 248 pets, and then the seconds have 2 of them, so we have 2 pets, so 2, 4, 6, 8, and add those. We add all the people who have 3 pets, all of their individual pets. I'm hoping that's kind of making sense. So in this sample, the total number of pets included was 14,752. The total people included was 4,023. When you divide that or set up that ratio, that's something I want to talk about, you get 3.66667 something, right? If you round that, you get to 3.7. If you round to the nearest whole number, you get 4. Why would it be important to talk in whole numbers? Typically, when we're giving a presentation, we want to be aware of what our number represents. In this case, it represents the number of pets owned by adults, ages 21 to 70 in this population. So most people don't own 7/10 of a pet, so 3.7 doesn't really make sense. You would want to say between 3 and 4 pets is the average. That's my personal opinion. However, if you're dealing with CEOs who deal with numbers and figures all the time, you could also include the exact decimal 3.7 or ratio, or however you'd like to present that information. Okay, so mu is the population parameter for the mean, and mu can be estimated, especially when you have a simple random sample of greater than size 30, which we have thousands, 4,023. You can take the sample mean, x bar, to estimate the mean for the population mu. So that's the whole bit for problem number 2. Moving on, almost done. Alrighty, here we go. So question 3 is asking you to think in terms of an interval and a point estimate. Thank you for your wonderful discussion, working with me and sharing with me what the course was saying. I was looking through the book and some of the resources I had. This one was pretty straightforward. This strategy was covered in our textbook or text manual, resource manual. The results of a survey show that the percent of adults in a certain town who want to change the name of the town is in the interval 38 hundredths to 41 hundredths, or if we thought of percents, 38% to 41%. That's the interval based on this survey. Well, how do we find the point estimate for the percent who want to change the town's name? Now, remember, the point estimate is something we could say is a good, like if we wanted a single number to represent the number of people who wanted to change the town's name. Mathematically, the way we find that is in our interval, we want it to be right smack in the middle. So you would add up your interval and then divide that by 2, and that will give you the middle number. It'll give you the midpoint, if you will. And it also gives you the point estimate. So we have, when you do that, you'll get 0.395 or 39.5%. So that's the point estimate. That's the statistic from the sample that you could use to think about part C. We'll talk about that in a second. Part B. What is the poll's margin of error? Well, there were several ways to calculate this. There was estimating the standard deviation, lesson 707. And if you want to review that, a closer look, standard deviation. This one is the half interval method. So you do exactly what you found here. You get your point estimate, and what you're going to do is you're going to take your upper range for your interval, your upper limit, so 41%. You're going to subtract 39.5%, or 0.41 minus 3.95. You'll get plus and minus, because the margin of error is on either side of the point estimate, right? We go up to 41% and we go down to 38%. So it's a margin of error of 1.5%. That's that's a nice close margin of error. That's good. We like that. And then part C is, do you think the town is most likely to change its name? Which statistic influenced your answer the most? Explain. So you get to tell me whatever it is that you want to say for part C is welcome. Try to justify it based on the math. You can be clever, you can be silly, but again, refer back to the data. If you were looking at this and you needed to provide resources to how do we get the name changed, are we going to hire people to come up with alternative names, do they vote on a handful of names, do they write in the name, how do we figure this out, right? So you have this data right here. Is the town most likely going to change its name? Which statistic influenced you and why? Like, just explain to me what you see. I'm going to leave it completely at that. If you say yes, just tell me why you think yes. If you tell me no, tell me why you think no. Try to refer back to what you see here, either the interval, the point estimate, the margin of error about this percent of adults in a town who want to change the name. So, all right. And would you want to change your name? That'd be fun. Tell me about a name of a town. If you could name a town, what would you name it? All right. Thank you for watching. Thank you for reaching out with questions. Thank you for joining me in live sessions. This is our last teacher graded assignment. Unless you're in honors, in which case you still have the project. You can also optionally complete the regular honor project in our class. Please reach out to me. Again, TGA for Unit 7 is done. Have some fun, turn it in, think about those big ideas, and look back. You have worked really hard, and I'm really proud of you. So it's been a blast being your teacher. We have a few more weeks, so I look forward to these last few weeks of finishing strong, reviewing for the final, and just all in all getting ready for summer and whatever we are off to next. So